Let's take a look at the field to finish workflow that will allow you to create an intelligent 3D piping model from a point cloud. Once you have the registered point cloud, we can use the following software to create the 3D model in the engineering documents: Autodesk ReCap, Kubit Virtusurv, Autocad Plant 3D, Kubit Pointsense Plant, and Autodesk Navisworks. First, we'll import the registered scan data into ReCap, which will convert the native file into an RCP file, which is then compatible with Autocad. Once you have created your ReCap project, let's import the native scan files. In this case, they are all FLS format, and ReCap will stitch the individual files together and create a seamless point cloud of the scanned area. You can see that ReCap has created spheres showing the location of the scanner during the data capture. This allows you to view both the point cloud and a high-resolution planar image of the area from each scan position. Virtusurv is a tool that comes with Pointsense Plant. Once our scans have been loaded, we can view the point cloud in a series of high-resolution planar images taken at each scan location. Virtusurv allows you to transmit points and coordinates from the planar image into any Windows application. Similar to the process used in ReCap, we load each of our FLS files into Virtusurv. Once the scans are imported, we can navigate through the point cloud by selecting a scan from the list on the left and viewing the image captured from that location. We can also switch views using the scan location map on the lower left. We can essentially use Virtusurv to walk around the area and take measurements from the scan exactly as we would using a tape measure in the field. We can also transmit the XYZ coordinate of any point directly into AutoCAD, allowing us accurate placement of components in our 3D model. Now we can start to create our intelligent 3D model from the point cloud using Autocad Plant 3D and Kubit Pointsense Plant. Once you've created your Plant 3D project, we can use Pointsense to import the RCP file that we created using ReCap. Once attached, you can navigate around the point cloud quickly and easily, just as you would an XREF containing typical AutoCAD solids. You can see that Pointsense Plant creates spheres in AutoCAD that correlate to the scan positions that we previously saw in ReCap and Virtusurv. Using the scan navigation function allows us to view the point cloud in AutoCAD from each scanner location, giving us a view of the point cloud at its most dense. Just like Virtusurv, we can navigate by selecting scan names from the list on the left, or we can click on the sphere from its geographical location. Once you've located the pipe run that you'd like to model, we load the Kubit Plant module and choose the appropriate pipe spec that we use to generate the intelligent Plant 3D model. Kubit comes with an extensive list of standard catalogs, or you can import your existing Plant 3D specs. Now we're ready to walk the run. To find a new run, pick 2 points along the pipe. Kubit's algorithm will process the data and return the diameter of that pipe. Once you determine that this is the correct size, Kubit will place the solid directly on top of the point cloud. The algorithm will continue to process points and place components along the run. In this instance, Kubit has detected a change in the diameter of the pipe in the vertical run and has automatically selected a 10x8 reducing T. As the algorithm continues to process, we're going to wait for it to return the next component, which should be a 45-degree elbow. And there we have that, and that component has now been placed on top of the point cloud. So we'll let Kubit continue to analyze the point cloud, and it should return the next component, which should be a 90-degree downward facing elbow. There we go. We can also place components manually on the point cloud using the Virtusurv tool to assist. By choosing points inside the Virtusurv photograph, we can transfer the coordinates back to AutoCAD. So let's navigate to the same scan position in Virtusurv and locate the components that you would like to place inside your 3D model. So what we'll do here is we'll take a look at this vertical run of pipe. And we want to know the last location of the location where that pipe run ends. And as you see, as you zoom into the point cloud, it gets more and more difficult to see the exact location on that weld. By looking at that point in Virtusurv, we can see that weld quite clearly. And we can use the points on that Virtusurv view, and it will translate that as coordinates back into our AutoCAD drawing, and you'll see that the coordinates selected have lined that pipe up beautifully. So now we'll continue on. We're not going to wait for the algorithm. We're just going to manually place. We know we have a 90-degree elbow to place, so we'll just place that elbow. We'll filter that by typing EL, and it will give us the 90-degree elbow option, and it will automatically place that at the end of the pipe. What we can do is we can't always determine the angle of the component. So again, we can go to Virtusurv, and what we can do is we can tell it to locate the angle of this elbow based on the coordinates that we see here. So by picking a few points along this weld, Virtusurv can analyze the coordinates, translate that back into AutoCAD, and you'll see it's created a circle that we can use to actually determine the angle. So there we go, we'll place that there. Now we'll see we continue on, we have a reducer. So again, we won't wait for the algorithm, we'll just take a look and yeah, here we go. Let's filter out for a reducer. So in some cases, you can't always tell exactly from information that you have what size that is. So when you're placing manually, you can scroll through the list of components and choose the one that you feel fits best on the point cloud. So we'll place that again automatically and continue on to place the flange. We'll just type in F, filter the flange. We can see the flange there, insert and continue. And we'll choose the valve. We can line the valve up. Again, this is something that you can look at manually. You can determine what the face of that valve is. You can see it there. It lines up perfectly with the point cloud. And then we'll continue on again. We'll insert that, and then we'll choose the flange, and it places that exactly. So you can see by the bolts that you can see in the point cloud that actually does line up. So now we can see the solid shapes sitting right on top of the point cloud. So what we're going to do is we're going to tie in, we're going to just put some equipment on here that I modeled earlier. So we can show the pump, and we have a support. And we're going to tie that pump into that solid line that we just created. So you can see that the way Plant 3D fits in with that point cloud beautifully. You can see exactly what that's going to look like once it has been constructed. So what we'll do is turn off the point cloud and take a look at the piping that we've just created using Kubit. So now we have to prepare that piping for Plant 3D conversion. And you'll see when you do actually create, there are little areas that don't quite line up 100%. We have to fix that before we can create Plant 3D solids, otherwise we're going to get those little teardrop leaks. So what we'll do is we're going to set the parameters. We're going to choose the line. Turning green shows that everything that we've selected is connected. And we're going to apply constraints. Now what the constraints does is it lines everything up as close to a vertical as you can get here. You can see it's going to straighten up the T, and it's going to straighten up the elbow. Once we apply constraints, you'll see a very slight shift. Everything should be lined up, and now when we export that to Plant, it should convert to Plant 3D solids without any teardrops. So we'll click Create to Plant 3D solids. We'll just choose that one line, hit OK, and pick the line. And you'll notice that it's dropped in the 3D shapes, the Plant 3D shapes, right on top of the Kubit ones that we modeled. So by hovering over that line, you can see right away that these are actually Plant 3D solids directly from the point cloud. They do have the spec data in there. They don't have line numbers because we have to obviously assign that line number. So what we're going to do is we're going to run an ISO here. So you can see by choosing a quick ISO, we're going to take a look at all the components that we created. And in the short time it's taken us to run Kubit, there's a completed as-built ISO of that line. We can see all the exact coordinate locations. We can see the valves and welds. We have a full bill of materials, all the locations, and you can see there that we have a cut list as well. So this is a very, very easy and effective way to as-built that line. Okay, let's close this down. So what we're going to do now is we're going to continue on with our new design. So we have our pump. I modeled some of the new scope piping earlier. Let's turn that on. And so we can see essentially where we're going here. So we want to have our new pipe tie into that existing pipe that we just created. So what we're going to do is we're going to mark this new pipe as being existing. Obviously, we don't want this to show up in our bill of materials and our scope of work for our small pump project. So we'll just turn that on to, we'll give it a status of existing. So now what we're going to do is we're going to continue on. We're going to take our existing cooling water, our new cooling water return line. I'm just going to grab that point, pull that over, and I'm just going to tie into our existing line here. It's going to be a really odd configuration. And here we go, it's done. And so now we're tied in. So our new design is tied to our existing. Let's continue this line on here and take a look. So we can see, we can determine what we were going to actually create here. So traditionally, when you're doing as-builting with modeling in solids, you can see exactly where the clashes are. So by taking that yellow line through there, we can determine by seeing where it hits that solid vertical run that there's a clash. And typically, you would have to have actually modeled that solid to see that clash. Now with the advent of the point cloud in AutoCAD, just by turning that point cloud on, we can take a look and we can turn around, basically we can rotate our whole model around here and see exactly how that's going to fit in with the existing plant. So we can see, just see there's a clash right here. So there's a bit of structural steel here. Let me just turn around so we can see it right there. So we can see that there's a structural steel clash here. And we did not have to model that structural steel, which saves a lot of time. So we know before we actually get into a fair amount of modeling that design is going to have to change. Either that steel is going to have to move in the field or they're going to have to rerun that pipe somewhere else. So let's turn off our point clouds. And what we're going to do is we're going to run a quick ISO on these lines. And we're going to see exactly where our new scope ties into our existing scope. There we go. Let's take a look at those lines. So this is the yellow line that we ran. And more importantly, this is the one that we tied in. So you can see the new scope as it comes from the pump into the existing line, which is now dotted. The bill of materials is only going to report new materials and new scope. Okay, so now it's time to create an orthographic view. And what we're going to do is create our drawing. Just give it a quick name here, piping. Okay. What we're going to do is we're going to determine the envelope that we want to detail. So we're just going to take this box, bring it down so that it only shows what we want to see. And we're going to drag that view into our ortho drawing. And you can see it's created the match lines for us, so we know exactly where that pump is going to be located inside the existing plant. Now, since our model is intelligent and we've assigned it real line numbers, we can annotate that view just by clicking on a pipe. It will query the database and it knows exactly what line number, size, all the tagging information that we have. If you do update your model, you can recreate these tags just by updating the drawing and everything updates with it. So you're still connected to the database at this point. Now that we've recreated some existing lines using Kubit Pointsense Plant and created some new lines using Plant 3D, we can verify the validity of the new design using Autodesk Navisworks. Let's take a look at clash detection using Navisworks Manage. We'll load our project RCP file and zoom into our work area. You can actually see that image is very clear. So let's append the piping model that contains our new scope of work. Now that our piping model is loaded, you can see that it blends in quite well with the point cloud, and you get a very good idea of what this project will look like once construction's been completed. The first thing we're going to do is isolate the line that we want to clash against the point cloud. In this case, we're going to isolate the cooling water supply line that we already know clashes with the existing support structure. So now we'll open Clash Detection and we'll create a new Clash Detection report. We'll select our existing RCP file and we'll clash that against our new DWG file. So now let's run the test and see how many clashes are returned in our report. You can see that we have 5 clashes highlighted. When you scroll through each clash in the list, Navisworks highlights the clash and zooms to the location in the model so that you can inspect it and apply a status. Once you've inspected all the clashes and updated their status, you can export the data to an HTML report, which can then be saved as part of your project records. Let's take a look at the output from the HTML file. You'll see the report includes a snapshot of the clash name, status, distance, description, date found, and the coordinates of the clash. The clash summary also includes a list of clashes which are new, active, reviewed, approved, and resolved.